Last time we discussed the phenomenon of molecules, discrete groups of atoms that make up many compounds and even some of the elements themselves. We've already discussed how Dalton observed that elements combine in whole number ratios to form compounds. And we just saw that when we account for this, we can explain why just a few different elements are needed to generate a practically inexhaustible library of materials that make up our universe. So we know that molecules exist, and that they're critical to explaining nature's incredible variety of materials. But the question still looms. What is it that binds atoms together into these molecules and compounds? Exactly how and why do they do this at all? The answer to that question is a phenomenon known as chemical bonding. To tell the complete story of our understanding of chemical bonding, we need to go back once again to the first decade of the 1800s and visit our old friend John Dalton, who asked the same question that we just did. How is it that various combinations of elements can create substances with these diverse properties? The obvious answer is that multiple atoms combine to form more complex structures with properties fundamentally different than those of the atoms comprising them. Consider the elements sodium and chlorine. One, a highly flammable metal, and the other, a toxic gas. Yet, in combination, these elements can form sodium chloride, which is also known as table salt, a non-toxic and even necessary part of our diet. Dalton did not have the benefit of understanding the structure of the atom, so he imagined that atoms somehow physically hooked themselves together to create small clusters of atoms that comprise compounds. He felt that this explanation would account for his earlier observation of the law of multiple proportions, which states that atoms combine in whole number ratios to form compounds. Simply defined, chemical bonding is actually an energetically beneficial interaction between atoms which confines them to a fixed distance from one another in space. The distance between two bonded atoms is commonly just an angstrom or two, not much larger than the radius of an atom itself. So we're talking about very, very close associations of atoms. When atoms get this close to one another, their electron clouds, being made from negatively charged electrons, can repel one another. So atoms can only ever get so close to one another before they start pushing against one another due to electrostatic repulsion. So we know why atoms can't get too close to one another, but the question still remains, why would they ever want to get close to one another at all? If all atoms' electron clouds push against one another, why not just keep their distance? What is the driving force that brings those atoms together? The energetic driving force that brings them together is the fact that all atoms strive to form valence octets. This powerful desire of atoms to have a full valence shell makes them willing to get close to one another when a mutually beneficial arrangement can be reached. When this is the case, atoms will stay within a specific distance from one another, a distance at which the attractive forces they experience are balanced by their mutual repulsion. This is the fundamental description of a chemical bond. Chemical bonds are actually a continuum, but are generally viewed as falling into one of three basic classes. Ionic bonds and covalent bonds make up the extremes, and polar covalent bonds fill in the gray areas in between them. There's also a fourth type of bonding called metallic bonding that we'll talk about today as well. So let's tackle each of these classes individually, and we're going to start with our extremes, ionic and covalent bonding. Let's start off with those ionic bonds. These are the sorts of bonds that are known to hold together many familiar substances, including things like table salt, which chemists would call sodium chloride. Other familiar substances like rust, also known as iron oxide, are also held together by these ionic bonds. In the case of ionic bonds, what holds atoms together at a fixed distance is electrostatic attraction. Electrostatic attraction results when atoms become ionized. And what is the driving force behind ionization? Of course, it's the octet rule. When we pair two atoms that have a tendency to form ions of opposing charges, there is a mutually beneficial exchange of electrons that can take place between them. So let's start our discussion about chemical bonding by considering two elements, sodium and chlorine. Now, we know that these combine in common table salt in a compound called sodium chloride, but why and how do they do that? And why is it so effective that we find this product very cheaply available to us? Well, let's consider them a little bit more carefully. We know from our discussion about trends in electronegativity and the periodic table, which contains this kind of information, that chlorine atoms are fairly electronegative, an electronegativity of about 3. Whereas sodium, on the other hand, is not very electronegative at all, with an electronegativity around 0.9. This means that chlorine is very, very eager to accept an electron, and sodium doesn't really care so much about accepting electrons. In fact, it really likes to let go of them. Remember, the ionization energy is actually quite low for alkali metals. So what happens when a sodium atom and a chlorine atom get close to one another? Well, an exchange happens that is mutually beneficial. Sodium likes to lose electrons. Chlorine likes to gain electrons. And so the outermost electron in the 3s1 shell of sodium can simply hop over to the chlorine and fill chlorine's third valence shell with an octet. And when this happens, the electron configuration of our new ions are neon and essentially argon, right? So our sodium has got the electron configuration of a noble gas. Our chlorine has also got the electron configuration of a noble gas. And this drives the bonding behavior of the two. It's the electrostatic attraction between them that causes this bond to form. Therefore, when a sodium and a chlorine atom are in very close proximity to one another, they can exchange one electron and create a very powerful attraction between the two resulting ions. But ionic bonds are not necessarily isolated connections between two atoms. When a mixture of ions like sodium and chloride ions get together, they can create a huge repeating structure known as a crystal lattice. This network of ionic bonds can stretch for billions upon billions of atoms and is so strong that in order to overcome it and melt sodium chloride, one has to apply temperatures greater than 1,000 Kelvin, higher than the temperature of lava as it exits Mount Kilauea in Hawaii. We're going to revisit the concept of the crystal lattice in later lectures, but for now let's concern ourselves with instead determining the empirical formula of ionic compounds. So we know now that some atoms like to let go of electrons to become positively charged ions, and other elements like to accept electrons to become negatively charged, and when that kind of preferential exchange happens, bonding occurs, ionic bonding. But how do we determine exactly how many of each of these elements combine to form ionic compounds? Well, we have to think about their charges. So let's think a little bit about ionic compounds and how they might form from different elements. Specifically, let's limit ourselves to the S and P block of the periodic table for now. So that gives us groups 1 through 8 of the periodic table. And I'm just looking at the first few rows here, but these trends should continue through all the columns and rows in the table, of course. Now, when we limit ourselves to the S and P blocks, there's a very defined trend in how ions form. Group 1 elements like to form +1 ions. Group 2 elements like to form +2 ions, and so on, until we get up here at about group 5, where the trend begins to reverse, with -3 ions common for nitrogen and phosphorus, -2 common for oxygen and sulfur, and a -1 charge common for fluorine, chlorine, and bromine. And of course, the noble gases, which get their name from the fact that they don't like to interact with other elements. So how can we use this trend to predict the formula of ionic compounds? Well, let's use a few examples. We'll do sodium chloride, magnesium oxide, sodium oxide, and magnesium chloride. All fairly common ionic compounds that you may find in the regular chemistry lab. Now, when sodium chloride forms, as we saw previously, a sodium +1 ion will get together with a chloride ion, which has a -1 charge. In this case, the plus charge of the sodium and the minus charge of the chloride ion cancel out perfectly, creating a neutral compound. So I would expect sodium chloride to have a formula NaCl. Now, magnesium and oxygen, they also have equal charges, in this case +2 and -2. So again, I expect equal amounts of them to be adequate to form ionic compounds. So when they join together, the formula that I get are NaCl and MgO. Pretty simple. But what about when I have a combination of ions that are not equally charged? How does that affect the ratio of elements in my ionic compound? For example, here's sodium oxide. Let's take a look at that one now. Sodium ions, we know, tend to have a charge of +1, whereas oxides tend to be -2. So notice here, I've had to pull a second sodium ion in to be sure that I end up with a neutral compound at the end of the process. What this means is that sodium oxide is expected to have a formula of Na2O, because it takes 2 sodium ions to balance the charge of 1 oxide ion. How about magnesium chloride? Let's do that one. Magnesium commonly forms 2+ ions, and chlorine, we know, tends to form -1 ions in the form of chloride. But we don't have charge balance yet. So, to achieve that, we have to have a second chloride ion, meaning that I expect the formula of magnesium chloride to be MgCl2. Now, when it comes time to take the test, there's a little bit faster way of determining this using a mnemonic that's related to the charges that we see. Let's do a few more examples to show how that works. We'll do aluminum oxide, we'll do sodium oxide, and we'll do calcium oxide. Aluminum tends to form 3+ ions, and we know oxygen tends to form a 2- ion. So in order to get a charge balance, all we have to do is take the charges on each ion and crisscross them and make them the subscript on the other element. For example, this becomes Al2O3. In the case of sodium oxide, we're dealing with sodium +1 and oxygen 2-, which means we make the formula sodium 2, oxygen 1, and of course we typically drop the 1 because we always understand when there is no subscript that we mean 1. So sodium oxide becomes Na2O. All right, now let's think about calcium oxide. We know that calcium, because it's in the group 2, tends to form 2+ ions, and oxygen, because of its position over here in group 6, tends to form 2- ions. So when we combine a Ca2+ with an O2- to get a neutral compound, all we have to do is have equal parts. Now, Ca2O2 would sort of be accurate, but we don't like to be redundant about things we already understand here. If it's an equal ratio, we simplify this down to CaO. So using this mnemonic, we can determine the formula of just about any ionic compound that we want, simply by understanding the common ionization states of the elements. Now that should suffice for our introduction to ionic bonding, in which electron exchange between atoms and the octet rule help to create oppositely charged ions held together by electrostatic attraction. But there are other types of chemical bonds. For example, yet another type of bond that we commonly encounter in chemistry is the covalent bond. The name itself gives us a hint to how these bonds work. Co, meaning together or shared, and valent, referring to the outer electron cloud energy level. Covalent bonds form not as the result of electron transfer, the way ionic bonds do, but as a result of electron sharing between two elements. Let's think for a moment about how this can happen. We know that atoms are always trying to find ways to fill their valence shells with an octet. And we've already seen the one way in which they can do this. Gaining or losing electrons in an all-out trade gives many elements a mechanism by which they can obtain an octet. But that comes with some limitations. Of course, the first is the buildup of charge as electrons are gained or lost, with no change in the number of protons in an atom's nucleus. We saw in a previous lecture how ionization potentials increase dramatically as each subsequent electron is removed from an atom. And at some point, it simply isn't going to be a feasible way to get an octet for everyone. To illustrate this, let's consider exactly where the lost electrons go when a cation is formed. In the case of ionic bonding, this problem is solved by a different element receiving the electron and forming an anion. This is a great arrangement in cases like sodium chloride and magnesium oxide because each of these compounds combines one very electropositive element with one very electronegative element. This makes electron exchange a snap. But what if two atoms have much more similar electronegativities? Now we have a serious problem. Electron transfer can't take place. Let's take a look at a few examples of atoms that can't form ionic bonds to one another and see how they cope with that. Let's take a look at an example here. Here's a fluorine atom, actually two fluorine atoms. Now, if they want to get together and form a chemical bond, we have a problem from the ionic perspective, don't we? That problem is that both fluorine atoms have identical electronegativities, 4.0. So there can't be any trading of electrons here. Who would accept and who would release? Right? Instead, we find ourselves in a situation where the two atoms are locked in a battle for electrons. They both want an extra one. So how do we resolve this and create a chemical bond between the two fluorine atoms? Well, in this case, they share. So our atoms are playing nice this time. Instead of one stealing an electron away from the other, they simply come together to a point at which they can share a certain number of their electrons. In this case, 2. So each fluorine atom has come close enough to the other that it sort of samples that extra electron that it needs without really stealing it away. So the atom over here on the left thinks it has 8 electrons. The atom over here on the right also thinks it has 8 electrons. So they both believe they have an octet and are both therefore satisfied. And this is what we call a covalent bond, a bond in which electrons are shared. Covalent meaning shared electrons. And in fact, we don't have to just have one pair of shared electrons. Consider oxygen atoms. 2 oxygen atoms suffer from the same bonding conundrum that the fluorine atoms did. They have exactly the same electronegativity and therefore aren't really inclined to release an electron in a transfer process. Instead, they're going to share. But because these two elements of the same electronegativity are short by 2 electrons in their valence shell, they have to share even more than fluorine did. In this case, when our 2 oxygen atoms come together close enough and share 4 electrons total, 2 from each atom, the oxygen atom on the left believes that it has an octet, and the oxygen atom on the right believes it has an octet. So they've once again fooled themselves into thinking that their valence shells are full without actually having to steal electrons away. And again, we call this a covalent bond, but in oxygen's case, because it's actually sharing 2 pairs of electrons, we refer to it as a double bond. In fact, certain atoms involved in covalent bonds can go even further than oxygen with their sharing. Atoms like nitrogen, which each have only 5 valence electrons, can come together to share 3 electrons from each atom, forming a very, very tight triple bond. It's this covalent triple bond of molecular nitrogen, or N2, that makes this gas so stable. And that is a good thing because each breath you take to give your lungs oxygen actually contains about 78% nitrogen. And unwanted chemical reactions in your lungs are generally not something you want going on. So we now have a basic understanding of the 2 more extreme forms of chemical bonds, ionic and covalent. We've seen how ionic bonds form when 2 elements of drastically different electronegativity, like a metal and nonmetal, get together and exchange electrons. In this case, one element completely relinquishes 1 or more valence electrons to another element, forming the ionic bond. At the other end of the spectrum are the bonds between two nonmetal atoms of the exact same type, and therefore the exact same electronegativity. These atoms can share pairs of valence electrons with one another to form covalent bonds. But we've left out one more case we need to consider. There's a third situation, the middle ground, in which we're dealing with 2 different elements whose electronegativities are similar, but not quite the same. Consider a bond forming between a hydrogen atom and a chlorine atom. Now, the electronegativities of these 2 are somewhat different, right? 2.1 to 3.2, but they're not drastically different the way that they were in our sodium chloride example, where it was 0.9 versus 3.2. So when a hydrogen atom and a chlorine atom get together, there is a tug of war over electrons, and chlorine's going to win, but it's not going to win outright. Instead, a type of covalent bond forms, in which, once again, our hydrogen atom thinks that it has a full valence shell, in this case 2 electrons, and our chlorine also thinks it has a full valence shell, in this case 8 electrons. However, because the chlorine is more electronegative, it doesn't share the electrons evenly with the hydrogen. Instead, if we were to look at this bond not as a Bohr model here, but instead simply as an electron cloud, what we would see is that the chlorine atom, because of its higher electronegativity, pulls more of that electron density towards itself, creating a region of denser negative charge within the molecule that results. And of course, that means that our hydrogen over here has less electron density and therefore becomes slightly positive, indicated here by the delta minus and delta plus. When this happens, we have a sharing of electrons, but it's unequal because of slightly different electronegativities. We call it a polar covalent bond. And we indicate the polar covalent bond by showing what we call a dipole. And dipoles are typically drawn in this way, as an arrow with a plus sign on the tail end of the arrow, indicating the direction of the positive and the negative sides. So far, we've discussed how the sharing of electrons can lead to covalent or polar covalent bonds. We used the Bohr model of the atom to demonstrate how bringing certain atoms into proximity with one another can lead to an energetically beneficial sharing of electrons. But we know that the Bohr model is an oversimplification. To really understand the structure of bonded atoms, we have to use all that we know about the electronic structure of the atom. To create a covalent bond, electrons are shared between two atomic orbitals that are overlapping, one from each atom. But not all atomic orbitals are created equally. And so the bonds that we can form are not always equal either. In general, there are two classes of covalent bonds that can form: sigma bonds and pi bonds. Sigma bonds are the result of orbital overlap directly in between two bonded nuclei on the internuclear axis. These kinds of bonds can form when either an s orbital or a p orbital overlap, having the shared electrons directly in between the two bonded atoms. This leads to a nice stable bond, so sigma bonds tend to be the first bond to form. But this creates a problem when trying to understand multiple bonds, like the double bond holding oxygen together or the triple bond from nitrogen. The problem is one of geometry. Only one set of orbitals can overlap directly in between the two atoms. But there are other ways to achieve additional overlap. See, the side-on overlap of two sets of p orbitals can also create a shared space that holds more sets of bonding electrons. We call these sorts of bonds pi bonds. And notice that the bonding electrons are not directly in between the bonded atoms this time. So pi bonds themselves, though stable, aren't as stable as sigma bonds. All of this means that when two atoms get together and form a covalent bond, the first bond between them is always a sigma bond, and any additional bonds are always pi bonds. Pi bonding is particularly important in the realm of organic chemistry, where carbon's ability to make up four bonds allows it to form very complex molecules in combination with itself and other elements. Many of these rely on the chemistry of pi bonds to carry out their important functions. So we now know that when a metal and a nonmetal combine at the atomic level, we tend to get ionic bonding. We also know that when two nonmetals combine, we often observe covalent bonds of varying polarity or no polarity at all, depending on the exact electronegativity of the two nonmetals. Now this leaves just one general combination of elements left: metal to metal. So let's think about metallic bonds for a moment here. Now, when we think back about covalent bonds, remember, when two nonmetals tend to get together when they have very similar electronegativities, they can share electrons with one another in order to fool themselves into thinking they have an octet. In the case of fluorine, that meant sharing one electron each. In the case of oxygen, 2 electrons each. And that's very easy for them to do. But imagine an element like, say, sodium or potassium. Now, these elements only have one valence electron, which means that they would have to get together with many, many other atoms and share many, many other electrons to get up to that point where they believe they have an octet. So sharing is not really a possibility. But of course, all of our potassium atoms in this example have exactly the same electronegativity, so ionic bonding is not a possibility either. They simply don't fit into any category we've discussed so far. But that's why we have our final category, metallic bonding. Potassium, when it bonds in this fashion, notice that I've put a number of these atoms together to create a sort of an array of potassium atoms, all of which have just one electron in their valence shell. But that's the important electron. So what I'm going to do now is sort of fill in the rest of the core of these atoms and just make that a sphere. So we can concentrate on what's happening in the valence shell of potassium atoms when they bond in a metal. My potassium atoms, again, have one electron in their outermost shell, but those shells can overlap throughout that array of atoms, creating what we call a valence band. one gigantic region through which all of these 4s1 electrons can move freely and unrestricted. So when I actually put these in motion, we can get an idea of what a metallic bond must look like. Notice the electrons are no longer belonging to one or even two atoms. These electrons have a free run of a gigantic region of this metal, and that is what makes metals so hard and so electrically conductive. It's because the electrons responsible for the bonds holding them together are running wildly all over the system. Now let's think about one other element that bonds metallically. Let's think about calcium. This is potassium's neighbor on the periodic table, one step to the right along a row. Now in this case, if we do the same exercise, creating our core and then creating our valence band, notice that there are twice as many electrons in that band, right? We have a 4s2 configuration, so now there are twice as many electrons, all with free run of that valence system. So calcium is much harder than potassium. This is an observable property that is a result of the fact that there are more electrons running through this bonding system, holding them together even more tightly. So this rounds out our tour of the most common types of chemical bonds that we're going to encounter in the course. Specifically, let's go over what we've looked at here. We took a look at covalent bonds, where electrons are shared evenly between two atoms, and how we have to have a very, very small, if not non-existent electronegativity difference between the two for this to happen. And that means that it tends to happen between nonmetals of the same element. Examples of these include the carbon-carbon bonds that are holding together the biomolecules in your body right now, the hydrogen-hydrogen single bonds that hold H2 molecules together, and the double-bonded oxygen that we're all breathing right now. The next type is polar covalent bonds, and these are formed from nonmetals whose electronegativity differences are considerable but not gigantic. So usually two different nonmetal atoms coming together to share electrons to fool themselves into thinking they have a full octet. Some examples of these include things like the NH bonds in ammonia, the OH and CO bonds that we find in alcohols, and the CN bonds that we find in molecules called amines, which are responsible for the foul smells in rotting meats. Now, if we move on, we think about ionic bonds, in which we have a very drastic electronegativity difference between two elements, usually greater than 2. And this means that they tend to happen between a metal and a nonmetal because they're at opposite ends of the periodic table. Some examples of ionic bonds that we encounter on a daily basis include the FeO bonds in rusting metal, or the NaCl bonds in the table salt that we eat every day. And finally, we talked about metallic bonds. Now, metallic bonds happen between two metals, whose electronegativities can be very similar. But it's not really the difference in electronegativity that drives metallic bonding. Instead, it's the fact that there just aren't enough electrons to properly share to make covalent bonds. And some examples of these include silver, sodium, and zinc. Practically any native metal that we come into contact with is held together by these types of bonds. So our short tour of bonding for this lecture is finally complete. So let's summarize. In this lecture, we turned our attention to what it is that holds molecules and compounds together. We discussed the definition of chemical bonding and how it's driven by the octet rule. We took a first look at how ionic bonds result from the exchange of electrons between and among atoms of greatly differing electronegativity, and how atoms of similar electronegativity can instead share electrons to fill their octets, creating a different class of bonds called covalent bonds. We brought our understanding of the atomic orbitals to bear on the issue of covalent bonding, seeing how stable sigma bonds can result from direct overlap between the bonded atoms, and how pi bonds form by the side-to-side overlap of p atomic orbitals, leading to the second and third bonds within multiple bonds. Finally, we considered how multiple atoms of the same metal might bond to one another, and we saw how their low valence electron count makes them unable to bond covalently, but that metals overcome this obstacle by creating a valence band through which each atom's outermost electrons can move, giving us a way to explain the hardness and electrical conductivities of metals. So we have a basic understanding of what bonding is and how it contributes to the formation of molecules and compounds. Next time, we're going to explore covalent bonding more by asking what happens when 3 or more atoms combine through chemical bonding to make more complex structures.